There is a photograph taken in 1984 that stops aeronautical engineers cold the first time they see it. It shows a Voyager experimental aircraft in a wind tunnel, and attached to one side of its fuselage is a full, graceful wing. On the other side, nothing. Just clean air where a wing should be. The engineers who commissioned that test were not documenting a catastrophe. They were asking one of the most dangerous questions in the history of flight. What if we only needed one? This is the story of asymmetric wing theory. The idea, pursued seriously and at great expense across multiple decades, that conventional bilateral flight was not an engineering truth, but an inherited assumption. And the engineers who believed it were not cranks. They worked for NASA, for Northrop, for DARPA. Some of them were right. Most of them were wrong in ways that took years to fully understand. And the lesson buried inside their failure remade how we think about the physics of the sky. To understand why anyone would chase a single-wing aircraft, you have to understand what a wing actually costs. Not in dollars, in drag. Every surface that meets moving air creates resistance. And in aviation, resistance is the enemy of everything: range, fuel consumption, speed, payload. A conventional aircraft is, in this sense, a compromise. 2 wings, a tail, a fuselage, each one solving a problem while simultaneously creating another. The engineers who began seriously investigating asymmetric flight in the late 1970s were not fantasists. They were accountants of aerodynamic debt, looking for a way to stop paying it. The foundational insight was deceptively simple. Lift, the force that holds an aircraft aloft, does not require symmetry. It requires airflow. If a single wing, properly designed and positioned, could generate sufficient lift across the entire span of an aircraft, then the second wing was not a necessity. It was a tradition. Remove it, and you eliminate not only its weight, but its parasitic drag, its structural complexity, its fuel lines, its control surfaces. You have the failure points of an entire wing system. On paper, the math was seductive. The most serious engineering attempt to validate this concept came through the work done around oblique wing technology, a concept pioneered by NASA engineer Robert Jones beginning in the 1940s and reaching its most serious experimental phase in the AD-1 program, which flew its first test in 1979. The AD-1 was not precisely a one-wing aircraft. It was something stranger, an aircraft whose single wing could pivot, rotating from a conventional perpendicular position to a dramatic angled configuration where one wingtip pointed forward and the other swept back at angles up to 60 degrees. At low speeds, it looked normal. At high speeds, it looked like a flying mistake. And yet, it flew. 84 test flights over 3 years, accumulating data that challenged nearly a century of assumptions about aerodynamic symmetry. What Jones had understood, and what took the broader engineering community years to absorb, was that swept wings reduce wave drag at transonic and supersonic speeds. Conventional aircraft achieve this by sweeping both wings symmetrically. An oblique wing achieves the same result more efficiently, because the asymmetric sweep reduces induced drag across the entire span simultaneously, without the structural penalties of separate swept surfaces. The single pivot mechanism was lighter than 2 independent wing assemblies. The aerodynamic efficiency gains, in theory, were significant enough to promise fuel savings on the order of 20 to 30% over long-range supersonic flight. The AD-1 proved the concept was survivable. It also revealed why it would not easily scale. The fundamental problem with asymmetric flight is not lift, it is control. When one wing generates more lift than the other, the aircraft wants to roll. When the center of lift shifts with changing speed and angle, the aircraft wants to pitch. Conventional aircraft solve these tendencies through symmetry itself. Whatever one side does, the other side mirrors it, and the forces cancel. Asymmetric configurations have no such automatic equilibrium. Every change in speed, altitude, or attitude requires active, continuous, computationally demanding correction. In 1979, the fly-by-wire systems capable of managing that correction in real time were either non-existent or prohibitively expensive. The AD-1 required its pilots to work harder than any conventional aircraft of comparable size, and the handling at high oblique angles was described by test pilots with words that do not appear in optimistic engineering proposals. NASA pressed forward anyway, because the fuel crisis of the 1970s had made efficiency a national security concern, and because the supersonic transport ambitions of the United States, humiliated by the cancellation of the American SST program in 1971 while Concorde flew in European skies, needed a new direction. A supersonic oblique wing transport could, theoretically, cross the Atlantic at Mach 1.4 while burning fuel closer to a subsonic widebody than to Concorde's profligate consumption. The study contracts went out. The wind tunnel models multiplied. A full-scale oblique wing research aircraft was proposed, designed, and ultimately never built, killed not by any single technical failure, but by the accumulation of unresolved compromises. Passengers, it turned out, were one of those compromises. An oblique wing repositions itself relative to the fuselage as speed changes. At cruise, one window row looks directly into the leading edge of the wing, while the opposite side sees clear sky. The cabin floor remains level, but the visual and psychological asymmetry was judged, in human factor studies, to be deeply unsettling. More critically, emergency egress from an aircraft whose wing geometry changes with flight phase presented certification challenges that the FAA had no existing framework to evaluate. These were not insurmountable problems. They were expensive ones, and in the early 1980s, as oil prices stabilized and the urgency of fuel efficiency softened, expensive problems had a way of becoming permanent shelving decisions. What survived was not the aircraft, but the understanding it produced. The computational fluid dynamics models built to analyze oblique wing behavior became foundational tools for aerodynamicists working on entirely different configurations. The fly-by-wire control logic developed to manage asymmetric lift informed the unstable aircraft designs, deliberately aerodynamically unstable, computer-stabilized, that became standard in military aviation through the F-117, the B-2, and eventually the entire fifth-generation fighter lineage. The asymmetric wing did not transform commercial aviation. It transformed the engineers who tried to make it work. There is a version of this story told as failure, and it is not wrong. No oblique wing transport ever carried a passenger. No airline ever ordered one. The fuel savings were never realized at scale. But that framing misunderstands what the exercise was for. Aviation progress has never moved in straight lines. It moves through the productive wreckage of ideas that were correct in principle and premature in practice. Ideas that exhaust themselves against the limits of their moment and deposit their knowledge into the substrate of the next generation's assumptions. The engineers who stared at that wind tunnel photograph of a one-winged aircraft and chose to take it seriously were not deluding themselves. They were doing what engineers do when they are working at the edge of what is known. They were finding out exactly where that edge is. And the edge, it turned out, was not aerodynamic. It was computational, regulatory, economic, and human. The sky would have accommodated the asymmetric wing. It was the world beneath the sky that was not ready. Every aircraft flying today carries, invisibly, the negative space of the designs that did not survive. The oblique wing is one of them. An idea that looked like a mistake, proved to be correct, and still has not finished being useful.